Thank you very much, Robert, for the kind introduction, and it's a pleasure to be here. In the next slides, I'm going to present our journey of, let's say, feeling old, or saying this, more than 10 years now working in this field of machine learning, AI, for medical imaging. Preparing for the talk, I thought about starting or showing or re-showing some of this. You have seen it. This picture, I think, was mentioned at the beginning of the session, the evolution of ImageNet and how basically we got to that superhuman performance. So you can imagine the year is 2010, 2011, and researchers on the ImageNet are competing in the range of 28, 26%. And then the year 2012, something happened, right, that the performance dropped now, or the error rate, sorry, dropped to 16%. So you can imagine being that researcher saying, oh my God, the gap is now 10 points below. And then people start realizing, yeah, going deeper is the way to solve the problem, adding larger networks and adding that more nonlinearities in the manifold of the data, right? Until the year 2015 with the ResNet, when that superhuman performance occurred, considering that the human performance was measured at 5% error rate. We, at the medical imaging side, we were also wondering, are we one day get there with superhuman performance, considering that the amount of data, considering that getting that amount of data is also a challenge by itself. And I'm going to touch base on that topic as well. So I want to start telling you our journey in that avenue of getting there. So this is on brain tumors. Our main focus has been on glioblastomas. So glioblastomas is a very bad disease that doesn't have actually an effective cure. The median survival is 16 months, and those who survive longer than 5 years is less than 0.5%. So the prognosis is really bad. Patients many times develop what is called a low-grade gliomas. They live for many years, and then they are transitioning towards a high-grade glioma. We just don't know when that happens, and then is where then you have this really bad outcome. During that process is where we use imaging for, well, diagnosis, the treatment, the preparation of that treatment, and the follow-up, right? So patients are called every N months, and then an assessment is done on that brain tumor. It's a very time-consuming process. Just so you have an idea, from the day of diagnosis until the treatment starts, in average, we are talking more than 17 days. Within that framework of time, 17 days, 70% of that time is used for delineation of these tumors, planning, and then an iteration between the radiation oncologist and the planner. Now, the task is really complex. It involves 4 volumes. What you see here are axial slices of one case. These are different MRI sequences that are required to really see the complete compartmentalization of that tumor. So a tumor has a necrosis, tissue that's already dead, an active rim, that's really active part of the tumor, an edema that is a combination of cell infiltration, but also inflammatory processes that are normal, as when you also have an injury, that's also happening in this case. Radiation oncologists, they need to delineate all this. Neuroradiologists, they also need to assess. In the lack of an automation here, what they would be doing is basically finding a slice that sort of characterizes the tumor, making a cross, measuring that product of diameters, and then making assessments every N months. You can imagine that if the patient tilted the head, then the whole metric just is completely off, right? So there's where volumetry has been always for many years, and we need on automation. All these aspects of time, all these aspects of basically, if a patient is not treated, within 3 months that patient is gone. So 17 days start becoming quite relevant. So there's been a whole community now since more than 10 years called BRATS, for brain tumor segmentation. This is a challenge that I think has been really good for the community because what we were saying that we need to compare, we need to benchmark methods, right? But also we need data that's made available, right? What you see here, these are the summary of the first years of that competition. On the left, you see the human performance, you see an inter-rater variability, and you also see the variability from the expert to the so-called consensus, right? And then the computer systems at those years were in this region, right? So what's green, you would say, legally is what you want your system to be within, right? That's kind of the human performance. You want a computer system to be within that performance. But clearly we see that these were the times of random forests, hierarchical support vector machines, and so on, right? The first neural network arrived in our field in the year 2014. And since then, as many other fields, we saw the performance improvement. What we have today goes in this direction of getting at that level of human performance, right? So here the colors indicate different years, and at the top we have those superhuman performance. What we have been doing is asking clinicians, do it your clinical way, maybe 45 minutes to 1 hour per patient, and then the superhuman way, which is spend as much as possible, which in practice happened to be around 3 hours per case. So those are the setups that we have used to benchmark our methods. Here I would make a pause and say, well, the models is super important to create the best possible models. I would say yes, but it's also very important to have a data-centric approach. As a matter of fact, after these 12 years of working on this, the better technologies we see are still systems like the UNet architecture. The UNet is at 8 years old CNN architecture that is actually difficult to beat. We still don't have transformers, with constant winning challenges. We see a lot of papers, claiming, but of course there is a publication bias and there is all the stochasticity we all know, right? And there is where the data-centric pipeline or data-centric mindset, in my opinion, had been more important than a model-centric approach. December 2022, we actually arrived to that FDA approval system. So we were really happy to see that all that work over those years, learning about the pitfalls of the systems, learning about the importance of a data-centric approach, in my opinion, paid off. This is a startup, it's a Boston-based startup. They call themselves a Bernese-based startup that integrates the technology we develop. We continue working on the new waves of models. This is a model for that task of glioblastoma segmentation, trained with over 3,000 subjects. Here I had to say, for all those data scientists here, that the painful part is data quality. And you might not like it because it's really boring and it's not the sexy part of data science, but it's really what has been fundamental in our journey. Data quality, data curation. We are still cleaning data. We still find issues with, here, this case kind of weird. We need to fix it. We need to actually retrain the model with cases like this. So I would say data curation and sampling and quality control has been mentioned by the colleagues. I would say, I would reemphasize that this is really, really important. This is how the technology looks like. So it's a companion suite that also has other type of data and so on. Here I could say, well, that's it. That's my talk. Really nice. We got to an FDA system level, but I would say no. Actually, FDA also uses metrics that are not showing us everything. FDA metrics also are based on metrics that are coming from the computer vision domain. Many of these metrics are actually not suited for clinical use or are based on an academic setup where, for example, average accuracy, average performance is what we all report in a paper, and we all call it SOTA. That's the new state of the art because my median or average value is better than the one last year. But I would argue that in medicine, many times robustness is way more important. And more than often, teams will overtrain a system to get to that super nice mean accuracy while trading robustness. So here's where we start talking about quality control of those systems. We talk about robustness of those systems, and comes the issue of the black box of neural networks. So I want to show here a quick clip that we prepared some years ago as a motivation in a workshop on the topic of interpretability in medical imaging. Some of the faces you probably will recognize.
There are many settings where a deep model trained on enough data that exhibits enough accuracy on test data is all you really need to go, and you don't need to be able to see what's inside that black box. However, there are other settings where that's a very risky thing to do, even if you've got what looks like superhuman accuracy on the test data.
I resent right now that the neural net wave and the deep learning wave has become so predominant that people say, well, that's the way to go. You just collect data and intelligence will work itself out. And that's just not true. I don't believe it. If you just take existing data sets and you put them into a machine learning system, the machine learning system will just copy the behavior of that data set. And if there's biases and it's been collected in unfair ways, then that will be replicated in the machine learning system and probably augmented because the machine learning system will be used over and over again. The initial bias will get replicated. How do you fix that? How do you think about that? What are the legal issues that are involved there?
You know, you just won't know about these problems. You wouldn't have anticipated them in advance if you can't sort of open up your model and see what's happening.
I think if we want to tackle some very complex problem, that kind of interpretability is necessary.
There's some AI people that say, you know, look, it's a black box, it does want to test that, why do you need anything else? I just don't agree with that point of view. I think this is a multi-stakeholder thing with many people that need to understand and all participate in their roles, and I think discrimination is critical.
Now, I'm okay using technologies I don't understand. I got here on an airplane and I don't fully understand how airplanes work. But I take comfort knowing that there is an entire field of aeronautics dedicated to creating that understanding. I would like to live in a society whose systems are built on top of verifiable, rigorous, thorough knowledge.
And we just find that every time we put on this magic glasses where we can see what's inside the model, we find an amazing number of things that are wonderful. But we also see things that are very surprising, very disturbing, and that no human would ever let get deployed until they found a way to fix it. And it's just so important to be able to put on the magic glasses in many domains and see these things before you deploy.
We are repeating this workshop I mimic on imaging and interpretability, and it's been for us really also a journey by itself. First, to convince many colleagues we actually need it. From an engineering point of view, many would say, well, if the system performs, why should I care? And many times there is where we have the so-called, or a phenomenon that's now understood as shortcut learning. So shortcut learning is actually a phenomenon that happens when the system is actually basically cheating on you as a developer of the AI system. The problem is solved, but some maybe spurious correlations are being used by that system. Right? And then it's really hard to catch those. And I'm going to show you an example of that happened in our own pipeline in this journey of this FDA brain tumor segmentation system. These are some publications showing cases of shortcut learning in medicine where you see that laterality markers are used by the system. These are typically emergency setups where you have a handheld device and there is a marker, and that those images are connected by pneumonia cases that are actually worse because they actually arrive on the emergency department, and therefore the model understands or learns that, well, if I actually catch that marker, I have better chances of optimizing that loss function. There's also this study in Lancet, which is one of the top journals in the field, also showing a study where interpretability was used to show that a system was actually able to recognize race, and then through the so-called saliency maps, those areas were actually used by the neural network to understand or detect race at a very high rate, as you can see now here. So this is what happens when you ablate that model. When you remove that area, you can see how that AUC completely plummets, right? So There are also now findings that show that neural networks see high frequencies we just don't see. So when we are actually using humans to annotate, and then we are using a data-driven approach that is rather uncontrolled, we have some loss functions, and some regularizations that we use typically just to facilitate training, many times there is where we just don't know what the system is going to be using as the so-called deep features, right? So I want to show you quickly our own experience in this field. So we were training a model that is able to classify between the low grade and high grade. What we wanted to do behind it was to say, well, if we have this automated identification of low-grade and high-grade gliomas, we could also train two distinctive segmentation methods, so then you have a pipeline there, right, of classify what it is and then segment that tumor. So we ran some of these saliency maps on those images. So what you see here is a quarter of the brain, and you see that tumor on an MRI T1 contrast, and you can see the T2, what's kind of more the whole extent, the edema part of the tumor. We ran those saliency maps, and we observed something like that in several cases where the model was actually catching or looking at the border. That border was synthetically added by us through our skull stripping process. So it's a brain extraction process that is used as part of the pipeline. The model actually liked that gradient and started looking and using those borders to classify the images. When then we realized why the model is doing that, we went through the whole pipeline, and this is the data-centric part again. We realized that our pre-processing was actually wrong. Our data normalization was using the whole image. We were using a set score normalization, including that background, as opposed to first normalize it just on the brain content. When fixing for that and rerunning those saliency maps, we saw a more plausible saliency map. As you can see here now, the method, the neural network was focusing more on the entity. Even more when looking at the AUC of the original model, we are comparing, and AUC was actually pretty good already, close to 0.9, and through this fix, we were able to then move it to 98%. So that was also a wow moment for us, saying these technologies, it's not only about understanding that many people claim, why do you care about understanding if it's so complicated and we don't even understand our own brain? Many times it's all about auditing a system and having tools to perform that quality control that otherwise would be rather difficult to do. Some other work we did here was what's the alignment between a human and that AI system? What is the system actually using when facing these 4 MRI sequences? And what parts of those images is the AI model using? So here's where it's a general approach of a data representation. We can also now use embeddings, right? And then have a feature importance block. Then the question is how we can trace back those features back to the pixel level per sequence. So what we did was a visualization technique that looks like a barcode here on top, where you see that features are sorted from left to right. The most important features are on the left, the least important on the right. Each row corresponds to an MRI sequence. So you can see that to classify enhancing tumor, the T1C, the second row here, is the most important, which aligns with the neuroradiologist. And the T1 sequence is kind of a helper sequence, so it uses less features, so less information is used from that. That also aligns with the neuroradiologist. And at the bottom, this was the very first time we were able to show what the neural network was seeing right in the data. So you see the input sequence, the MRI, and then next to it, that's one selected deep feature by the model. So we could actually have a conversation with the doctor about what the neural network is doing. So alignment between human and the expert. And there are also legal reasons. GDPR also has some articles about the right to explanation, and so you can check it out at the European level as well. I want to very quickly, since I'm running out of time, very quickly also show you that it's possible to use interpretable information to boost the performance of the model. So what this is also called XXAI or explainable AI that boosts performance model. And this is based on this publication on a concept we call SIPNet that uses saliency maps as an inductive bias. So an inductive bias is basically a way to regularize or to guide that model during training. What we realized was the following. If you have a neural network and you have, let's say, classification of classes, of diseases, what we can do here is generate those saliency maps. Then we realize, but actually we can generate it per class. So if I have 5 outputs, I can generate 5 of those saliency maps. If each of these saliency maps corresponds to a specific disease, they should be different as well. So in a way, as we do self-supervision with deep features saying, well, they represent different things, therefore they should be more distant, well, does it work with also saliency maps that are actually a fingerprint of models' gradients? So that's what then we did here, was to start measuring the distance of these so-called saliency maps or model fingerprints, and then building losses around it to then promote that distinctiveness and promote some special properties. So the kind of the look-alike of those saliency maps. We want them very concentrated, or we want them sort of spread, right? That's where the medical knowledge comes into place, right? The cool thing about it is that it's self-supervision. You don't actually need label data. So you could start with supervision, then you turn off your cross-entropy loss or whatever you're using, and then let these laws guide the rest of data that's not labeled. So we did experiments with, there is a data set called the Shakespeare data set. Here I'm going to skip this to show you 2 things. One is the quality of those saliency maps resemble more what the expert would do. So you see the hand-drawn saliency maps on the left, and then here is the different competitors and SIPNet with this regularization on this class distinctiveness I showed. And of course, performance, you want also better performance since those deep features are being better guided. So here is different proposals, the way we exploit those interactions on that graph I showed you. Since I'm running out of time, I'm going to quickly jump to this slide that I think is the important on the multimodality. So the black box of interpretability, we could say that is actually enlarging since we aim, and in medicine is actually a science that requires multimodal and requires also longitudinal data. Many of the diseases or the assessments of a progression of a disease or the disease is stable is based on a percentage. And that requires us to start thinking about foundational models that are both multimodal and also longitudinal. So the black box is actually getting more complex. So here comes the question answer, maybe is, can we actually use an entity to help us understand or orchestrate those interactions? So imagine the following: you have task-specific or modality-specific models. This orchestrator is going to interact, and it's going to be kind of a translator of what those models are doing, right? So imagine it like your own chatbot that can interact with MD, and the MD can also challenge that the decisions of those individual or modality-specific AI systems. So we are in the now makings of creating these systems. Now we are really baby steps on imaging plus text reports, and we are contented with that at the moment. But then the challenges are basically, again, quality control. The data, multimodal data, is extremely sparse, and let alone when we start considering longitudinal data. So as a home take message, my message is data-driven pipelines, human-centered AI approaches are really important. XAI is not only about understanding or explaining. I believe it's also information we can use to better guide models, and also for quality control and verification. And this verification of this model guidance basically is thinking about what is the use of this segmentation, what is the use of this classification, how good it has to be, and what are the risks actually that is something it's less sensitive and more specific, for example. So I would say for data science purposes, it's very important to say what is the right metric and what would be the actual clinical metric that ideally we should have, and is there any kind of proxy to that? And then finally, in this enlargement of the black box, maybe here we have all the LLM possibilities where there is an orchestrator entity that can help clinicians and us as developers to better understand the dynamics of this data flow. Thank you very much for your attention, and happy to answer any questions.
Hi, very cool talk, thank you. I have a question regarding the saliency method. So in the last years, there have been a couple of results kind of showing that essentially they're unreliable, and also in cases act more as edge detectors than actually, showing with the signal. How do you evaluate that you actually,
Yes.
capture the right things? And it also it seems contradicting the results, right? Because you get better models.
Yeah, fully agree. I think there are 2 to 3 aspects to consider. Some of these aspects are on the evaluation itself of that. So there is a very cool paper from Alex Binder on CVPR last year, where he actually points to some of these pitfalls. And one of these pitfalls is, for example, if you perturb an input and then you expect the output to also change in a silencing map, right? But when that doesn't happen, people start getting nervous that it's not sensitive enough. But then the logic should follow that you perturb what actually matters. And many of these studies, some from Google, from the team of Bin Kim, which I love, it's great questions, but there's the caveat that, or the nuance that the perturbations are being made across the whole image. So if a model is not using information of a given pixel and that pixel is perturbed, we actually should not expect any change in the silencing map. Some of these observations, like edge detector-like, I also think that there is the human bias, and it's this disagreement or this misalignment between human features and deep learning features. And there's where we have a big problem of those deep features that are not aligned with the human. How do we actually evaluate them? Is this new knowledge that we should embrace, or we should maybe take it more slowly because this is the new thing that the neural network discovered? Silencing map also have had assumptions, and we were discussing over the coffee break about ReLUs. So why do we actually not let negative gradients go through? And the assumption, and I have checked the literature, is that positive attributions is actually meaning importance. But when you talk to a doctor would say the absence of something is also good when they are performing differential diagnosis. They said, this is not that, because if it was, I would see that, but I don't see it. So in the development of silencing graphs, there is a called guided GradCam and guided backprop, and so you also have those assumptions that I think could be revisited for applications like medicine. Yeah. I think it's an evolving field. I see that some of this information is also a proxy. So rather than using it directly to specify this is what the neural network is using, I think could also be seen more, this is information that could be used maybe in a different fashion as presented here to help us.
One more question. Quick one. Thanks again.
Thank you.